I want to talk a little bit about some initial work we've done to move us towards a situation where researchers are more readily able to identify and reuse computable phenotypes relevant to their work. I have no disclosures. First, a quick definition of computable phenotypes, which I'm sure you'll be aware of. These are knowledge objects which use a patient's EMR alone to determine if they have a disease or condition. And what we're seeing is the emergence of what we call phenotype libraries, which are online catalogs of often thousands of computable phenotype definitions. And what we're seeing is from among those definitions stored in libraries, many actually target the same disease or condition. So for example, if I type diabetes into the phenotype knowledge base, I'm going to get 34 results. And if I type diabetes into the HDR UK phenotype library, I'm going to get 161 results. So there's a slight caveat to that 161, which we'll talk about shortly. But in general, the takeaway here is that there is evidence of a significant number of phenotypes in these libraries targeting the same disease or condition. Now, in general, this is mostly a good thing. It's not desirable, and even if it was, probably not feasible to have a single computable phenotype for every condition. And the main reason for this is different use cases, for example, research use cases or clinical use cases, they necessitate different logic that sits behind that computable phenotype, what we might often know as the phenotype definition. However, with this, what we call phenotype definition multiplicity phenomenon, we need to understand the space of phenotypes that we have. We need to understand which use cases are already supported in these phenotype libraries by the definitions that are stored. And we need to do that because that then supports reuse. So without that understanding, it's very hard for research to identify which computable phenotypes are relevant to their use cases. We can flip this around and say that what we need to do is to understand what is unique about each phenotype. Because again, if we understand what's unique about each phenotype, we can understand which use cases it best supports. And then what we can do in turn is take this information and store this as metadata against these phenotypes in these libraries to make this available to researchers. So this is the situation that we want to move towards, or we started to try and move towards in this work. So how do we identify what's unique about each phenotype? Well, we thought that to do this, we can actually start by doing the opposite. We can actually understand what's common between two computable phenotypes. How do they intersect? Because obviously, if you understand the intersection, you can then understand what's unique. And we aim to do this automatically and therefore at scale. Two barriers to this automated intersection analysis that we were planning on doing. The first is that when identifying two computable phenotypes that target the same disease or condition, it might actually be difficult to do that in the first place before we even get down to comparing their logic. It might be difficult to work out when two phenotypes are actually trying to identify the same disease or condition. This is because the naming conventions used for these phenotypes within these phenotype libraries often differs. So for example, in the phenotype knowledge base, we might find one type 2 diabetes phenotype referred to as T2DM implementation, and another referred to as just type 2 diabetes mellitus. And it's difficult, therefore, to know, it's not straightforward to know, are we targeting the same disease or condition? The second barrier is once we've actually identified groups of phenotypes that identify the same disease or condition, how do we then within those groups compare those phenotypes to see if there's any intersection in logic? Because if we're working purely at the computable level, there's going to be different forms of these phenotypes. Traditionally, phenotypes might be codeless that are perhaps applied in something like Python, but we can also find more complex implementations, so phenotypes that are actually realized as natural language processing processes, for example. Then the challenge becomes, how do we actually compare these different implementations? To solve the first problem, to identify groups of phenotypes that identify the same disease or condition, first of all, we looked at the names of various definitions and compared the text similarity there using Levenshtein distance. To complement this, we then also leveraged the HDR UK library API, to which you can submit a keyword, in this case the name of a condition such as diabetes, and you can get back all the other stored definitions that have that keyword. And what we hoped, what we aimed, or what we hypothesized is that would give us a broader collection of phenotypes that are related but don't have a high text similarity. As I alluded to before, through the fact that when I search for diabetes, I get 161 definitions, what we saw here is just because a keyword appears in the existing metadata of a phenotype in the HDR UK library doesn't mean it's necessarily connected. We get, in other words, a lot of false positives. So the third step of this method to identify groups of phenotypes that target the same condition was actually to use a large language model to validate the phenotypes that were returned in step 2 here. So to check, look, this additional phenotype has this keyword, but is that because the keyword just happens to appear in the metadata, or is it actually a connected condition? To solve our second problem in terms of comparing definitions that have different computable implementations, we leverage the Phenoflow technology, which we've previously developed, which takes computable definitions and abstracts them up to their common logic and does this in a step-based approach using the common workflow language. What that then enables us to do is to abstract away from any individual implementations and look purely at the logic, look purely at those steps in that logic, and compare those instead to determine intersection. What did we find? Well, we first of all loaded 1,171, so just over 1,000 definitions into the Phenoflow library, and then we analyzed the names of those definitions as per the methods given to identify condition groups, so groups of computable phenotypes that all target the same disease or condition. We found 137 condition groups, so conditions with 2 or more phenotypes, and we did some validation among the authors and got a positive predictive value there of 95% to validate that these groups did indeed contain the correct phenotypes. We found that 574 definitions existed as part of a group, so just under half. So what this tells us, what the takeaway from this result is, what we could discuss from this result, is that the definition multiplicity phenomenon is a real thing. This is good insight into the extent of it, in the sense that over half the definitions that we had actually had a duplicate in the corpus of phenotypes that we looked at. Our second result in terms of intersection, so actually looking at what is the common functionality or logic between the phenotypes within individual groups, we actually saw a trend that across the 10 largest condition groups shown here on the right, the average number of steps in common between pairs of definitions, so if we compare pairs of definitions, the average number of steps in common relative to the average number of steps in the group is low. So for example, for diabetes, if we do across all pairwise comparisons of definitions, only about 11% of steps are in common on average relative to the average number of steps in the group. So what does this tell us, this trend that we saw across the example here of the 10 largest condition groups? Well, it tells us that while definition multiplicity is certainly a thing, there are still a number of definitions on average. In general, definitions still have a considerable number of unique steps. So because this intersection was relatively low, that means conversely that there's a number of unique steps. So in other words, it's worthwhile taking this information and keeping this as metadata that can then be used by researchers. Our final result was in terms of the impact that the use of a large language model had. We observed, for example, that the large language model allowed us to identify false positives that might have otherwise been included. So matches between phenotypes for different types of heart failure, for example, could be excluded by that additional knowledge that's brought by the use of a large language model. And alternatively, it allowed us to identify false negatives. So we might have had phenotypes, for example, that targeted the same condition and would have been excluded by text similarity, but were actually retained from this keyword search, because although they maybe didn't mention the condition by name, they maybe mentioned something related to the condition, such as medications. So in summary, the use of Phenoflow has allowed us to compare definitions and understand more about definition multiplicity, which we saw to be extensive. So lots of, as we thought, we've now been able to quantify this and show that there are indeed lots of definitions that target the same condition. But in reality, what we saw when we did this intersection analysis was actually the overlap in logic between those definitions was relatively low. So in other words, there is unique functionality which is worth drawing attention to. And the adoption of an LLM improved this process. Future work will actually take this metadata and apply it to the Phenoflow definitions in the Phenoflow library. And it will look to also not just look at definition intersections, so horizontal relationships, but also look at subsumption relationships as well. So vertical relationships will be explored next. Here's some links. So there's an implementation and the data analysis, all documented for open science, and you're welcome to visit Phenoflow there at this link.